Hello everyone. In this video, we will continue talking about the secant method. We will talk about the halting condition of the secant method, and then I will show you an example about how to use the secant method to find the root of a function. The halting condition are very similar to the halting condition for the Newton-Raphson method. There are three different conditions which may cause the iteration process to halt. The first one, we halt if both of the following conditions are met. So there are condition A and condition B, and both of them should be satisfied. Condition A is that the step between successive iterates is sufficiently small. That is, the absolute value of xn plus 1 minus xn should be less than a constant, and this constant, we call it epsilon step. And condition B is that the function evaluated at the point xn plus 1 is sufficiently small. That is, the absolute value of f xn plus 1 is less than a constant, and this constant, we call it epsilon abs. So this condition is very similar to the first halting condition for the Newton-Raphson method. Condition A is that when we move based on x0 and x1, we find x2, and then we move from x2 to x3, and then from x3 to x4. When we move from xn to xn plus 1, the distance between xn plus 1 and xn is so small that we barely moved. So there is no point to iterate again. So the condition B is that the function evaluated at xn plus 1 is sufficiently small. We need to check this because for some function, it increases so fast around the root, and when we are a little bit away from the root, the value of the function becomes very large, and then it's not safe to say that this point is a good approximation of the root. So that's why we need to check the absolute value of f xn plus 1 to make sure that it's small enough so that we can say xn plus 1 is a good approximation of the root. The second halting condition, if the denominator is 0, then the iteration process fails because we have this division by 0 problem, and then we halt. Remember that the formula for the secant method looks like this. So xn plus 1 equal to xn minus fxn times xn minus 1 minus xn over f xn minus 1 minus f xn. Okay, so this f xn minus 1 minus f xn is the denominator. It's possible that sometimes f xn minus 1 is exactly equal to f xn. If that happens, the denominator becomes 0, so we cannot continue this iteration process. All right. The last halting condition is that if we have iterated some maximum number of times, say n, and haven't met condition 1, which means the process didn't converge within a number of iterations, then we halt. So this method belongs to the open method, so there is no guarantee that this process will converge. So sometimes by using secant method, we can find the root, and sometimes we cannot. So we always set up a maximum number of iterations we want to do. If it doesn't converge within this number of iterations, then we assume that this process will not converge, and then we stop this iteration. We either change to a different initial approximation of the root, or we change to another method. All right, so if we halt due to condition 1, we state that xn plus 1 is our approximation to the root. If we halt due to either condition 2 or condition 3, we may either choose a different initial approximation x0 and x1, or state that a solution may not exist. At least by using the secant method, we cannot find the root. All right. So then let's see an example about using the secant method to find the root of an equation. So example 1, perform 3 steps of the secant method for the function f(x), which is equal to x squared minus 2. We start from the initial guesses, x0, which is equal to 0, and x1, which is equal to 1. So let's see the first iteration. Okay, so let's draw a table. Assume that at the nth iteration, we have xn minus 1 and xn, and based on xn minus 1 and xn, we want to find xn plus 1. Okay, so when we start, n is equal to 1, and we have this xn minus 1, which is x0, which is 0, and we have this xn, which is x1, which is 1. So we need to, based on these two values, to find xn plus 1, which is x2. So according to the formula, x2 is equal to x1 minus fx1 times x0 minus x1 over fx0 minus fx1. Okay, so x1 is 1, and fx1 is 1 squared minus 2, which is negative 1, and x0 minus x1, which is 0 minus 1, this is again negative 1, and fx0 is 0 squared minus 2, so this is negative 2, minus fx1, which is negative 1. All right, so this will be equal to 1 minus negative 1, so this should be equal to 2. So x2 equal to 2. So let's do another iteration. So when n is 2, we have xn minus 1, which is x1, which is 1, right? And xn, which is x2, just move the 2 here. And then based on these two values, we want to find xn plus 1, which is x3. So x3 equal to x2 minus fx2 times x1 minus x2 over fx1 minus fx2. Okay, so x2 is 2 minus fx2, which is 2 squared minus 2, which is 2, and times x1 minus x2, which is 1 minus 2, so it's negative 1, and over fx1, which is negative 1, minus fx2, which is 2. So this should be equal to 2 minus negative 2 over 2 minus 2 over 3. So this should be 4 over 3. So this is 4 over 3, which is x3. So when n is equal to 3, we have this xn minus 1, which is x2, which is equal to 2 and then x3, which is equal to 4 plus 3. Then we need to find x3, right? So x4. So x4 is equal to x3 minus fx3 times x2 minus x3 over fx2 minus fx3. So this will be equal to x3, which is 4 over 3, minus fx3, which is 4 over 3 squared minus 2. So this is negative 2 over 9 times x2 minus x3, which is 2 minus 4 over 3, which is 2 over 3. Then over x2, fx2, which is 2 minus fx3, which is negative 2 over 9. So this will be equal to, so you can calculate this using a calculator, and this finally will be 7 over 5. So it's 7 over 5 here. All right, so this is an example about using the secant method to find the root of a function. In the next video, we will talk about how to implement the secant method in MATLAB.